So the motivation behind this talk is there's a lot of different resources out there about, hey, here's how you tune vacuum, here's how you do this around vacuum. I've never seen anything that actually goes into the in-depth, nitty-gritty detail of what the heck is vacuum? What is it actually doing? Why do we need this thing? So that's the goal of this talk, is to give you the actual fundamentals of what vacuum is doing, how it works, why it works, so that when you start reading advice on, well, set your vacuum cost delay to this, you understand what is that actually doing. As such, the talk's going to be very in-depth. It's going to be actually looking at some of the code. I do have reference, where applicable, to the actual sections of code in the presenter notes, so when we get the slides posted to the conference website, you'll be able to download them and see the detailed reference points. This presentation is written for specifically against Postgres 9.4. I don't think there's any significant changes to 9.5, but if you are running an older version of vacuum, some of what I say here may not apply, so just be aware of that. This is the laundry list of everything we're going to go over. So show of hands, who knows what Mvcc is? Good, awesome. We'll go over that very quickly then, talk about some of the other aspects around that, recording when transactions have been committed or not, and then get into what can actually be vacuumed before finally getting to how does vacuum actually work, and then finally auto vacuum. So Mvcc, if any of this isn't clear, please ask a question, but I'm going to breeze through this very quickly because everybody seems very familiar. In a nutshell, Postgres, when you do a delete, you don't actually delete the data. You just mark a little bit on the disk that says, hey, this transaction deleted it. The second part of this is that when you do an update is essentially an insert, and you delete the old row and you insert the new row. That's ultimately why we need to vacuum, because when you change data in Postgres, the old data stays place in the table. The second part of this is, okay, we mark something as deleted. Well, we mark it with a transaction ID. People that then visit this row later, and this is true of inserting rows, they need to be able to say, hey, I've got this row with transaction ID 59. Did that transaction commit, or did it abort, or is it still running? So the C log, the commit log, is what tracks that for you. It records whether a transaction committed, aborted, or whether it's still in process. Multi-transactions work, the back-end infrastructure is very similar to the commit log. They're there for a different purpose. They handle pieces of information that are stored with rows of data, just like the commit information, but they need to handle multiple transactions accessing a row at the same time. Normally, you will only see this with foreign key checks. That's the big use case, but there are some other scenarios that can get into that, which I'll get into later. Vacuum is what's responsible for removing data from C log and the multi-transaction log. So it does more than just shrink, keep your table size and hopefully your index size in line. It's also responsible for some other parts of the system as well. So one of the key questions, one of the key ideas you need to understand how vacuum works is this question of what data can actually be vacuumed? What is safe to be removed? And generally speaking, you can only remove data that was deleted by a transaction that is older than the oldest running transaction in the database. There's a few things that kind of alter that. The biggest one of those is hot standby, streaming replication. If you have hot standby feedback enabled and you have a long-running transaction on one of your streaming replicas, that prevents vacuum from removing data on the master. So you have to be cognizant of that if you enable that feature. From a detailed standpoint, there is a special lock that we have to acquire on the page level, on a shared buffer level, before we can actually remove any old data from that page. It's safe and normal for other backends to hold what's known as a buffer pin, not the same as a lock, but a pin on a buffer, potentially for a very long period of time. For example, if you have a query that's doing nested loop joins and there's several levels deep, that outer nested loop could hold a pin on a page for minutes, possibly tens of minutes, heck, possibly even an hour. So normally for every other part of the system, Bruce, correct me if I'm wrong, I believe no other part of the system cares about this besides vacuum. Vacuum does care though. Vacuum, in order to safely remove data, there can be nobody else holding a pin. So that's an important concept that I think a lot is probably not very well known, is if you're sitting there and you're going in and vacuuming and going, well, the bloat's not really going down, this is potentially a cause. And this is one thing that changed in 9.5. We now actually will spit out log information when we can't acquire this lock. So the key takeaway here is long-running transactions and high transaction rates, not good, because long-running stuff means vacuum can't do its job.
Are there any other type of common pins that are taken out that prevent vacuum from running?
There's a bunch of other locking considerations that can come into play. Like if you, for example, if you've got an exclusive lock on a table, you can't vacuum it. But I think that most people are a bit more familiar with those. Obviously, you can't vacuum something if it's still in the process of being inserted or deleted. So those kind of locking, I think, is more commonly understood. It's this buffer pin that most people don't. I'll get into that later, but at this point, it's all the same thing. It's right.
So you mentioned you enable feedback and certain other parameters on the replicate. If you don't want vacuum to remove data.
Yes.
Is that only 9.2 or is it also available in 9.3?
Do you remember when we put that in? Hot standby feedback. So probably around 9.2. Well, the hot standby feedback has been an option for a while. It gives you the most capability to run queries on a streaming replica. If you don't have that turned on, there's other things you can do to try and prevent query cancel on the replica. They're just not as effective. The flip side is hot standby. That's going to have the greatest impact on your master. Freezing. Anyone ever run into oh, holy cow, I need to freeze my database because the transaction's going to wrap around? Transaction IDs and MX IDs are simple, unsigned 32-bit integers. And the assignment of those is a counter. Because we need to handle things both in the future and in the past. In reality, you can only have the database can only effectively track 2 to the 31st, so 2 billion transactions at once. As you start approaching that 2 billionth transaction, we need to do what's called freezing, which is we go through and every single transaction ID from an insert record that has been committed, we have to go and say, look, forget the transaction that committed it. Everybody can see the row. It's going to just be special transaction ID, I think it's number 2. And that tells the system that this row is frozen. We know that everybody in the entire system can see it. active freezing, if you have a high transaction rate, can become very problematic. And on today's hardware, I think we've actually, I know we've demonstrated use cases of having to freeze more than once a day. I don't know that anybody's that bad in actual production, but I mean, that's what you can end up with. And if you've got a large database, that becomes very problematic. So this is something that you definitely need to keep track of if you have a high transaction rate. Not only that, but if you start burning through multi-transact IDs, which normally is done with concurrent foreign key checks, that can also cause you a problem. And this is something else that I think, how many people know about transaction wraparound? If you haven't experienced, yeah, so almost at least half the room. How many knew about MXID wraparound? Yeah. So you need to be careful. This is a bit of an unusual workload. I don't think that MXID wrap is nearly as big of a danger in the real world, but be careful. If you've got something that you do tons of foreign key checks concurrently, high concurrency, keep an eye on this. In terms of actual, so now that's kind of, here's why we have to do this and here's how we figure it out. In terms of actually being able to get vacuum done, there's been some improvements that have been made over the years. The first one that was made, and I believe this was 8.3 or 8.4, so this has been out for a long time, are heap-only tuples. So the idea here is that when you update a row, if the update does not touch any fields that are referenced by an index, there's a special way that we now perform the update that allows us to go into that page and remove the dead row when possible without having to touch the index. And that means we can remove that dead row without running vacuum. So, which is just far cheaper than going through the full vacuum process. So the big thing to remember here is when you can, avoid referencing heavily updated columns in an index. And when I say referencing, obviously that means an index on the column, but it also means if you have a where clause on the index, or if it's a functional index and the column is referenced by the function. If you can avoid doing this, this means that you can take advantage of hot updates in the table, which really helps reduce the need for vacuuming. This is especially important for tables that have a very high update rate. So if you've got a very common example is a queue table. If you're trying to track, hey, here's some work that needs to be done, and you're updating those rows frequently, try not to index the rows that get updated heavily so that you don't have to actually vacuum, you can use hot. So vacuum itself, there are 4 variations on vacuuming. Auto vacuum is a built-in process that tries to just, hey, you don't need to worry about any of this stuff. Probably 95% of Postgres databases, especially more recent versions, auto vacuum, it just does its thing and you don't have to worry about it. Auto vacuums become quite good. The problem you run into is when it doesn't work, now you have to start digging into what's going on. Vacuum full completely rebuilds a table from scratch. It's honestly not terribly useful because it takes an exclusive lock on the table while it's running. So I'm not really going to cover vacuum full. Vacuum is just a regular manually run vacuum. Vacuum freeze is a vacuum that sets the freeze limit for that vacuum to be basically 0. So it will try and freeze everything that it can. If you are in danger of a wraparound, you might want to run a vacuum freeze. The other place where a vacuum freeze can be very handy is if you have just loaded a whole slew of data and it's all been loaded in roughly the same transaction range. If you proactively freeze, you get all that data frozen, and now you don't have to worry about sometime in the distant future, 2 billion transactions from now, the system's going to go, wait, I need to freeze everything. I need to freeze 10 terabytes of data that you just loaded. So it gives you a lot more control. Auto vacuum. As I said, it's pretty good in 9.4. You generally don't have to mess around with the settings. Previous versions, some of the settings were not so great. In particular, the vacuum threshold. For a while, I think it was set to 0.2 or 0.4, 20 or 40%. That was pretty bad. But generally, you don't need to mess around with it. One thing to be aware of is you cannot control when auto vacuum runs. There's been some discussion of trying to put some controls in place, but there are none. Some people have mistakenly thought, hey, I know, I'll set auto vacuum nap time to be 1 day, and that means it'll only try and vacuum once a day. And that might work for a little while when you very specifically restart your database to restart that counter at, say, midnight. But over time, that's going to start shifting and skewing, and then eventually it's going to be vacuuming in the morning and then in the afternoon. Or if you have some kind of an emergency and you have to do a restart during the middle of the day, because when there's an emergency, we always think with a very clear head and we never forget anything. Now you go, oh, hey, and then it says, hey, auto vacuum, so now you have another emergency because the auto vacuum you've been trying to avoid kicks off. So just don't do it. There's other ways to tweak auto vacuum if it's causing problems. Worst case scenario, you can actually turn it off, but don't try and do it with nap time. If you have a workload for your site, for your system that is cyclical, either every night is a slow period or maybe the weekends are slow periods, it can definitely help auto vacuum do its job a lot if you just schedule a regular plain old manual vacuum to run even just once a week. Because that vacuum, it's running during a slow period, you can potentially make it more aggressive, especially with the freeze settings, that it tries to get stuff done ahead of time so that while you're during your peak period, you don't suddenly have auto vacuum going, oh, I need to freeze this 10 terabyte table. The last thing that you can do to really help auto vacuum out is if you have a table, again like a queue table, that just sees a lot of update traffic, just go ahead and schedule a cron to just vacuum that thing. I've set it up and run in production where it vacuums once a minute, depending on the update rate. The reason that you want to do this is that, and this is especially important if it's a heavily updated table that should normally also be very small, like a couple hundred, couple thousand, maybe 100,000 rows. When that table is small, it's very fast to scan it, it's very fast to do the updates, it's very fast to handle it, and the vacuum itself is going to be very fast as well because there's not that much data to try and deal with. If vacuum isn't happening aggressively enough on that table though, it's going to start getting bigger and bigger and bigger, and now you run into a problem where your site is slow, you've got other problems, you're going, well, how do I shrink this table? And now you can't, it's very hard to shrink the table because ultimately you're going to have to do something like a vacuum full, and that's going to take an exclusive lock, and hey, it's going to take a long time to run now because the table's big. So, vacuum full, as I said, I'm not going to talk about it very much. It did change in 9.0 prior. Is anyone running anything older than 9.0? So prior to 9.0, vacuum full, it did something very different. that if you run a vacuum full, it's going to bloat the heck out of your indexes. So we at least did fix that. Basically now what it does is it runs a create table as, it creates a brand new copy of your table, rebuilds all the indexes, and then says, here you go, it's all nice and pristine. It's a great way to remove bloat. It's starting in 9.0, but the big problem is it takes an exclusive lock. If you're in a situation where you're going, oh, I need to run vacuum full, and you don't want to pay for that exclusive lock, the PG Repack project that you can find at that URL or search for it on GitHub is meant to alleviate that problem. And what PG Repack does is it goes ahead, it creates a new table, it puts a trigger on the old table to record changes that are happening while it's copying data to the new table. So it copies the data, builds the indexes, it finally goes through and deals with everything that changed while that process was happening. You end up with two tables that are completely identical, and then it takes a very short exclusive lock to drop the old table and rename the new table. So it still has to take this exclusive lock, but it's very, very short in duration. Do be careful though, there's an older project called PG Reorg it's dead code. I believe there is a link on the project that points you at PG Repack, but just make sure you've got the right project that you're looking at. Vacuum itself. So a lot of this will translate into auto vacuum. I do have a section after this about auto vacuum explicitly, but at this point I am talking specifically about a manually run vacuum or vacuum freeze. One thing to be aware of is you cannot run a vacuum in a transaction. So if you're writing, ETL, something like that, and you want to say, hey, let's do a vacuum freeze after I load all this data, that's a good thing to do. You just have to make sure it happens outside of the transaction. There is a vacuum DB shell command. So for doing like a database-wide or even cluster-wide vacuum via cron, there's a shell command that just makes it easier to do that. What vacuum actually does is for every table that it's told to vacuum, you can either give it a list of tables or you can say vacuum the whole database. Goes to each table, it scans the heap, the table itself, remembering what tuples need to be removed. Then it scans the indexes, removing those tuples from the indexes. Once it's done with the indexes, it goes back to the table itself, removes those dead tuples, and then finally, if you specify the analyze option, it goes and runs analyze. The very last thing that it does is it updates the frozen information at the database level for both transactions and MXIDs. So if it was able to do freezing and advance your freeze age on a per table basis, it always records that at the table level, but then if it did that, it goes and updates the database level as well. Key thing, yes?
Does all that spit out the statistics in the log file when you do the verbose?
Yes, sort of, kind of. If you know how to read the verbose, you can follow what it's doing, and I could almost do an entire talk on just reading vacuum verbose. So the answer is yes. One very, sorry, go ahead.
Yes, auto vacuum also in the workers runs analyze as well when it's finished.
It uses different thresholds, but let me get to the auto vacuum section. One really key critical thing to understand is that the way vacuum works, if there's any indexes on a table, it has to remember what tuples are dead, then hit the index, then go back to the table. How many tuples it can remember is driven by maintenance work mem. So if your maintenance work mem is not large enough, it now has to scan through all the indexes on a table more than once. So always, always, always be careful about your maintenance work mem. Make sure it's not set really low. Honestly, on pretty much any production server hardware you're going to hit nowadays, I just set that to the max, which I think is still 1 gig, and just leave it there. So the vacuum command, when you type in vacuum, it calls the vacuum function. Vacuum function does a few things, and then it calls vacuum relation. This is the function that actually vacuums a single table. It does a bunch of mundane housekeeping stuff, and then it either calls cluster relation if you said vacuum full, or it calls lazy vacuum. Before returning, it calls itself to vacuum the toast table. Toast is when you do a text field, varLNA, anything that can be very large. If you have values that exceed roughly 2K, they get put into a separate table called a toast table. That toast table has to be vacuumed separately. So that is the last thing that vacuum rel actually does, is it just calls itself again to say, hey, now go vacuum the toast table. The bulk of the work actually happens in lazy vacuum rel. So we've gone from the vacuum command, which calls vacuum relation, which says, hey, we're doing a lazy vacuum, which is a normal vacuum, not a vacuum full. And now we're doing the actual work on one single table, either a regular table or a toast table. First thing it says is it decides, it looks at the statistics for that table in PG class, looks at the frozen transaction ID and the frozen MX ID, and then looks at our current transaction and MX IDs and says, do I need to freeze this table? If the frozen transaction point for that table is close enough, it's going to say, guess what? This vacuum is going to be a freeze vacuum. We're going to do extra work. We're going to scan the entire table and make sure that we freeze as much as we can. Once it figures that out, it calls lazy scan heap to actually scan through the heap, the table itself. If we were able to remove, to mark entire pages at the end of the table dead, then it will call lazy truncate heap to try and actually shrink the size of the table on disk. It cleans up the free space map, and then finally it will update PG class to indicate that it did the vacuum and if it was able to advance the freeze ages. Lazy scan heap, this is the function that actually walks through a table looking for things to vacuum. So for each, and probably 80% of this function is just a giant for loop. So for each block in the table, if we're not freezing and there's at least 32 consecutive blocks marked in the visibility map as being all visible, it's going to start skipping ahead. So if you have tables that are insert mostly, or maybe they get updates and deletes, but it's always like, say, at the end of the table, this can be an enormous time saver for vacuum because it just says, hey, here's a whole slew of table of pages that are all visible, which means I have nothing to do. Unfortunately, if we're doing a freeze vacuum, it cannot skip all visible pages because just because the page is all visible, it may still have rows, tuples that need to be frozen. If we have almost run out of work mem, then it's going to go kick off the function that scans through all the indexes. Again, going back to what I said earlier, make sure work mem is big enough to remember all the dead tuples in a table. Finally, so now we know that we've got work mem available. We've got a page. We want to actually go vacuum this page. It tries to acquire that cleanup block. If it is not a freeze vacuum and it cannot acquire the cleanup block, it just skips the block and moves right along. If it is a freeze vacuum, we have to scan every single page. So freeze vacuum, it's going to sit and wait for this lock. Now, you might be going, well, this is silly. Like, why are we running a vacuum and then we have to skip? This was actually changed, I think, in somewhere after 9.0. What used to happen is we always waited to be able to acquire this lock. And remember that a page pin could be held for a very long period of time. So what would happen prior to this change is you'd have some long-running query that's holding a pin on a page. Vacuum comes along and says, hey, I want to clean this page, so now it gets in line behind the long-running query, and then you start having queries that come in and say, hey, I want to pin the page too, even if it's just for a select. Well, they now start waiting in line behind the vacuum. So you've got long-running query, and then vacuum, and then if it's bad enough, every other connection in your entire database is waiting on the vacuum that's waiting on the long-running query. So that's why we made the change. The idea here is that this is probably a very infrequent thing. I don't know if it's infrequent or not. So we now have logging in 9.5. If you run vacuum verbose, you'll see if it's a problem. Please, if you see the log that shows up in a vacuum verbose that says, we had a bunch of pages that we couldn't vacuum because we couldn't get the lock, let the community know, because we need that feedback. There's more sophisticated things we could try and do here, but we don't want to do them to solve a problem that doesn't exist. Once we've got that cleanup lock, we prune the page, which is the same thing that hot does, and I'll get to that in a bit. We record the tuples that got removed, so now we're using that maintenance work mem that we have. We update the free space map, and if the page is now entirely visible, we update the visibility map. That's block by block by block, going through the table, go back to the for loop, start again. Finally, once we fall out the end of the loop, we've scanned the entire table, we update the statistics, and we make the last pass through the indexes to clean up the index tuples. Speaking of cleaning up index tuples, lazy cleanup index is the function that does that. The way that you do vacuuming for an index depends entirely on the index method. Postgres is extensible enough that you can actually create new index methods. There are 4 that I can think of off the top of my head. The way that vacuum operates on each one of those is slightly different. And again, I could certainly give an entire talk on how all those work. So basically, it varies depending on the index. The critical thing to know is it's very difficult to reduce the size of a bloated index. It's hard to do it for a table. It's basically impossible to do for a B-tree index. I'm not sure about the other index types, but I'm pretty sure it's very difficult there as well. So this is the biggest problem you will run into if you let your database get bloated. It's not even so much the bloat at the table level, it's the bloat of the indexes that it's almost impossible to just get rid of. So if this happens, you're going to basically be stuck either just living with it, which indexes are usually much smaller than the table, so that may be a valid option. Or if you can do a vacuum full or use PG Repack. Finally, last step in the overall table vacuuming process, last major step, is lazy vacuum heap. So all these dead tuples that we've been remembering using maintenance-free memory, this is the step that walks through that list and goes back to the pages and says, oh, hey, remove this one, remove this one, remove this one. It does the actual table level work. It also defragments the page, and it records how much free space the page has in the free space map. Finally, update dat frozen XID. This is called by vacuum. So lazy vacuum heap, we were vacuum rel, we were 5 levels deep. Now we're all the way back up to vacuum itself, where it all started. It's basically the last thing that vacuum does. It updates frozen, the frozen markers for the database. And if it was able to update those, if any tables got frozen during the vacuum run, it truncates the commit log files. It updates the internal frozen XID and MXID information. There's copies of this that are stored on disk, and then there's copies that are stored internally in shared memory. And finally, the multi-exact files are not truncated by vacuum, but the next time a checkpoint runs, that's when those get truncated. And I think we may be changing that in 9.5 or 9.6. But that's the end of the actual vacuum process. So, questions on that before I move to auto vacuum?
If it's terminated at any point, is all the work lost? Or?
It depends on where it's terminated. So, if it hasn't scanned the indexes, it's basically all gone. If it has scanned the indexes, then those index scans, that work is committed in effect as the scan happens. So if you've gotten to the point where it's scanning through the indexes, whatever work it does there in the indexes, that work is okay. That doesn't really help you too much because it's just going to scan the index again. It'll save you some writes, but that's it. If you are unfortunate enough that it has to make multiple passes through the table, once it scans the indexes and then starts going back to the table to remove the dead rows that it remembered before it starts looking for more dead rows, all of that work is saved. So at that point, whatever it removes out of the table, you're okay. If you manage to cancel it or it gets killed right at the end of that process, you basically haven't lost anything. If you are running multiple tables, so that's all per table. If it's a vacuum that's running multiple tables, whatever tables were successfully completed their vacuum, they're done. It's really just whatever table was in the process of being vacuumed when it got killed. So, any other questions on vacuum internals?
Just one thing, I think if you terminate it, even though it did all the heavy reading and writing, you'll still miss getting relevant frozen XID.
Yes. Yes.
So the next time you run manual vacuum, and the next time auto vac sees that table, it's going to want to do the whole end-to-end scan again.
Yes.
So immediately don't cancel it if you can get away with it, but if your system's hosed, we do this sometimes where I work. We do go ahead and kill them, and we just take whatever we got and let whatever happens happens.
Right. So the key thing there is that for a vacuum freeze, if you're trying to freeze the table, either manually or vacuum just said, hey, we're close enough to the threshold, that to advance the frozen pointer, where that table is, the vacuum of that table must complete in its entirety. If it doesn't, you may have vacuumed stuff, but you didn't move the freeze pointer whatsoever. So yeah, that's a very good point. All right, auto vacuum. Much of what auto vacuum does, the guts of the vacuuming process, it's essentially the same as the manual vacuum. Most of what auto vacuum is, it's built on top of vacuum. There are two different parts, two different back-end processes that comprise auto vacuum. There's a launcher and the workers. So the launcher, every time the launcher cycles through, it looks at every database that you have in the cluster. If there is any database that's in danger of an XID wraparound, boom, that's the one that's getting vacuumed, that's getting a worker. If there's any database that's in need of MXID wraparound, that's the next priority. If neither of those conditions is true, then all it does is it looks at the least recently auto-vacuumed database. The one caveat here is if every database was vacuumed at least vacuum nap time seconds ago, we're done. We don't need to do anything. Once it has a list of, hey, here's databases that I would like to launch workers for, it goes and sees if there's workers available, and if there are, they'll be fired up. Multiple workers can work on the same database at once. So if you have auto vacuum configured to have 10 auto vacuum workers, they can all work on one database at a time, one database at the same time. One thing that is different about auto vacuum versus manual vacuum, nothing in the system is going to cancel a manually fired vacuum if it starts affecting things. Auto vacuum, on the other hand, if auto vacuum is doing something and it's holding up other parts of the system, it's holding a lock that some other part of the system needs, that auto vacuum will automatically get terminated by the system. The idea here is to make auto vacuum as inobtrusive as possible, but if this is something that starts happening repeatedly on some table, now auto vacuum effectively can't vacuum that table.
I don't think that that's true if it's an auto vacuum prevent wrapper. I think that will...
True. Yes, good point. If the auto vacuum was triggered to prevent wraparound, it is a much more aggressive vacuum. Auto vacuum that is preventing wraparound is effectively the same thing as if you called vacuum freeze by hand. It still uses the auto vacuum cost delay settings instead of the regular ones, but other than that, it's as if you'd done it manually. So how do you know if auto vacuum is being effective? A good way is to look at how many auto vacuum workers are actually running in your cluster versus the auto vacuum max workers setting. If you sit and monitor that over time and you see that you're always using all of your auto vacuum workers, that's a pretty good indication that auto vacuum may not be keeping up to date with the work that needs to be done. So at that point you need either more workers or something else to help alleviate the problem. So auto vacuum launcher, it does its thing. It says, hey, here's databases, and let me get some workers fired up. So each worker, it gets a list of the heap tables and materialized views that need vacuum or analyze. It gets a list of toast tables. Now, normal vacuum, when you say vacuum table, it does both. Auto vacuum is a little more intelligent and says, well, if the toast table doesn't really need vacuuming, I'm just not going to vacuum it. Or maybe the heap table, I can't see why the heap table would not need vacuuming, but toast does, but if that happened, it's able to do that as well. One important thing, auto vacuum cannot vacuum temporary tables because it doesn't have the access and the visibility it needs to do that, because it's all stored locally in the back end that created the temp tables. So if you're doing heavy stuff with temp tables, and especially heavy updates or deletes in temp tables, you probably want to issue a manual vacuum against that temp table. Once it gets a list of tables that it says, hey, I'd like to vacuum this table, it attempts to get the vacuum lock. This is not the buffer cleanup lock. This is just, I need a shared lock on the table. If it cannot get that lock because there's DDL or something else running that's blocking it, it just says, oh, okay, and goes on to the next thing. So be aware that if you run DDL, especially DDL commands, there's probably a few others that might do this, but if you run those kind of commands very, very frequently, you could end up making auto vacuum ineffective. Finally, once it's gone through and vacuumed every table that it identified it wanted to vacuum, it updates the frozen XID just the same way a manual vacuum does, and it exits. It does not sit there and loop. figures out the tables it wants to vacuum at the front, hits those tables, and then it's done. And now it's up to the auto vacuum launcher to say, oh, hey, we need to vacuum this database again. Also, auto vacuum does not prioritize tables within a database. So whatever order it looks at them in, and I think it happens to be OID order, that's the order it's going to vacuum them in. So if you have a table that's in desperate need of vacuuming, it may end up at the end of the list of auto vacuum, and then if auto vacuum does something and the worker gets killed, well, guess what? That table's still at the end of the list. Auto vacuum can become ineffective if you have high demand, for high demand tables, if too many large tables need to be vacuumed at once. So by default, I think we have 3 auto vacuum workers. If you have 3 multi-terabyte, you know, hundreds of gigabyte tables, and all of them suddenly need to be vacuumed at the same time, all your auto vacuum workers can easily end up stuck working on those, and nothing else is getting vacuumed in the entire cluster until at least one of those finishes. There are a number of different settings that are available for tuning vacuum. I think that the documentation on all of them is pretty good, and I'm basically out of time anyway, but I will point this out for vacuum cost delay. This is the most likely parameter that you'd want to tune. The idea here is that once we hit the cost limit, we sleep for the delay period. So every operation that vacuum performs, if it reads a block, that has a cost. If it reads a block that's in shared buffers, that has a lower cost. If it writes a block, that also has a cost. Every time it does one of these things, it increments the cost, and when we hit the threshold, vacuum says, okay, I'm going to take a nap. And by default, I think it's a 10 millisecond nap. So if you want to slow vacuum down, you can increase the vacuum cost delay. Be careful though, because if you slow vacuum down too much, yes, your vacuum, it doesn't have as much impact on the system, but guess what? That work still has to be done. So if you slow it down too much, vacuum can't keep up, you're bloating the database, you're just making the problem a lot worse. So be very careful with how much you slow vacuum down. If you have a system that has a very good I/O system, for example, a built-in RAID controller with a battery-backed cache that allows you to do a write to the cache of the RAID controller and then the write immediately returns, in those scenarios, you should set the page dirty cost to be lower than the page miss cost. The reason for this is that the write is ultimately going to be very cheap because you're just hitting the cache on the controller. Yes, it's going to have to get written out eventually, but there's a bunch of stuff that can be done to tune that. The page miss, on the other hand, if the page isn't in, and keep in mind, that's a mission in Postgres shared buffers, but if the page comes out of OS buffers, it's still going to be pretty fast, but we're going to consider it a miss. So keep that in mind. But if the miss actually is not in the OS buffers either, now you have to read the page from your storage, and there's no way to ameliorate that cost. It's going to be however expensive it is. So especially if you're on spinning media and you've got a write back cache, you probably want to flip those. So in closing, the takeaways, the big takeaways. Don't have long running transactions if you have a high transaction rate, because those in vacuum don't mix. High transaction rate, use of for share lock and concurrent foreign key checks increase your need to freeze. It's not just your transaction rate, it's also these other things that affect the MX IDs. Indexes referencing heavily updated columns prevent hot. Make maintenance work mem high enough so that you don't have to have multiple passes through a table. It's very difficult to reduce bloat, so try not to let it happen in the first place. And auto vacuum can only do so much. There are things that you can do that will really help it out. Unfortunately, I am out of time, but if you do have any questions, I'll stick around probably in the back or outside, and you can always drop me an email. Thank you very much.
Jim, there's also no talking here next because we're going to lunch.
Oh, hey, all right, well, I'll just stick around in here, so.
It's kind of free form at this point.
All right, questions?
How much of what you were describing would not apply to version 9.3?
I think 9.3 is going to be pretty close. I don't think we made any significant changes in 9.3. I think we did in 9.2. 9.2, I think the biggest change is that's, I believe, where we put in the change to the locking behavior. Other questions?
You've got a streaming going. What impact of that? What things can create negative issues, if you will, with that feedback?
Right. So the problem that you run into with vacuum and streaming replication is that streaming replication, it's binary level. It's not logical, it's the bits on the disk. So if the master does a vacuum and is removing these rows, and you have a query on a replica that's trying to read that old data because it's an old enough transaction, well, now you've got this problem. So you can either just say, well, kill the freaking query on the slave, or you can say, well, hold up the replication. So don't replay the vacuum on the slave, but now your slave is falling behind. Or you can do the hot feedback, which means that the slave is periodically pushing information back to the master to say, here's the data that I'm accessing that you cannot vacuum. If you turn that on, then from the standpoint of vacuum, it's as if that query was just running on the master. So whatever that thing is doing in terms of visibility,
We've got a case where we just have not allowed the transaction to cancel. We're using the standby to actually decision.
right.
And so we don't, and that's customer facing. So we can't say, oh,
Right.
just kill that transaction.
Right. Now,
Kill
if
that transaction out. The transactions are 50 milliseconds or less.
on this on
the standby.
I wouldn't worry about it. If 50 milliseconds is going to affect your vacuum, please give me a call because I'd like to take a look at what you're doing.
I mean, that's the way they're real life.
Yeah, no, it something on the order of seconds, probably even minutes.
And no, like if you're doing some type of analysis, even if it takes 5 or 6, 10 seconds, that can impact potentially, but something that's under 100 milliseconds, you're not going to really know.
Yeah, well, and there is a, the feedback provided to the master is not immediate. It's only done on a periodic basis. Oh, well, it's advancing the age. So yeah, it would still, it can, yeah, basically there's a delay in there. There is a config setting that controls how often that happens, and I think by default it's probably like 10 or 15 seconds anyway. So anything shorter than that, you're not going to see.